So AIML, the first module is just theory mostly. We'll go through it really quickly. Agents perceive the environment through sensors and act upon it through actuators. So there's an environment, there's an agent. They take in information through a sensor and they act upon it using an actuator. A few examples are given there. Humans have eyes and ears as their sensors, hands as actuators. They also have three characteristics. The first is rationality, which is you choose the path that gives you more success. So you want to maximize that success. Second is autonomy, which means that these agents can act on their own experience and knowledge. And third is reactivity, which means they're able to quickly respond to a change in the environment or a change in the user input. The second is environments. There's four characteristics here. In terms of agents, the first is performance measure, the second is environment, the third is actuators, and the fourth is sensors. So for a taxi, a performance measure would be safety or it would be speed. Environment would be road or traffic. Actuators would be steering or brakes, and sensors you can see are camera, speedometer, etc. So there's a few types of environments. The first is full or partial environment, which means these sensors can see the full environment and, well, in partially observable environments, they can't. So a fully seen environment is chess. Poker is something that you can't observe everyone's action or everyone's like cards, for example. Second is deterministic or stochastic, which means the next state is always dependent on a combination of the current state and the action that you take as an agent. Example of this is traffic signal. An example of stochastic is that it's random and unpredictable. You can't really predict the next state based on the current one. The third is episodic or sequential. Current state has some sort of dependency on the previous state. So that's a chess is again an example of that. The fourth kind is static or dynamic environments. That is, these environments change as the agent tries to come up with an action to take. So let's say you're a taxi on a road, you're trying to think whether to go right to left, then the traffic is going to change around you. So the environment keeps changing. The fifth is discrete or continuous. Here. So environments have finite states or infinite states, pretty simple to understand. In continuous, they have infinite states. So examples are tic-tac-toe and basketball. The last is single versus multi-agent, whether there are single, like whether there's one agent or multiple agents in the whole environment. There are a few types of agents as well. The first is simple reflex, and this is just the most rudimentary agent. It reacts only to the current state, doesn't care for any consequences. So you can see a small diagram that is you enter a condition and its action is based on the sensor's information that it processes. The second is model based, that is, there's a percept history and an internal memory. And these can work in partially observable environments. So to update an internal state, this model has to do two things. Firstly, it has to observe how the world changes upon its action. Second, it has to know how its actions are going to affect this world. So small diagram here as well. The one on the left here, that is, it takes in the current state and the condition as well, and it operates based off of that. The third is a goal-based agent. That is, you operate based off your aim. That is, you want to reach a goal, and that's why you're going to choose an action. This requires searching and planning. So let's say you have a location to get to. You're going to use Google Maps. That probably operates off goal-based. I don't know, goal-based. It's goal-based. The fourth is utility-based. Basically, it takes a goal-based agent and it further optimizes it. So you create a best way to reach it. So there's also a factor known as utility or happiness in the diagram on the right here. So you add a box there and say, oh, this is a utility-based environment. Sorry, agent. The fifth one is a learning agent. It learns from past experiences. So here there are a bunch of features of performance evaluation. It's going to learn, it's going to receive feedback and operate based off of that feedback. But also finally, it's going to generate new problems for the agent to learn more. The last bit of theory in this module, or just the last bit of this module in general, is percept, sequence, and the agent program. So the first is percept sequence, is just a complete history of the agent's actions at any point in time. So let there be an agent that's a vacuum cleaner, for example, and there are two squares that can move in, A and B. And it can do two things. It can perceive the square it is in, and if there is dirt in that square. The second is it can choose to go left, right, it can choose to suck, or it can choose to do nothing. Now, we describe this behavior with an agent function by mapping this sequence to an action. So let's say the sequence is two actions, A, comma, clean. So you look at the box that you're in, the square that you're in, and you see if it's clean or dirty. The first two are that. Then as you go on down the sequence, you'll see that the same sequence is often repeated. So I'm not sure why, but it is repeated and it's probably useful to remember. I'm not sure if they've even asked this, but yeah, it's there. Um, the final thing is an agent program, and it's the underlying app working mechanism. So it's just 2 to 3 lines of code explaining how the whole thing works. So it's just like Python code at this point. If status is dirty, then return suck. If else if location is A, then return right. Else if location B, then return. That's pretty much it for module one. Now module two, which is problem solving. So there's a bunch of theory in the beginning. Problems are unwelcome situations. You probably want to generate alternatives and reach a goal state. A transition model is used to model these problems. It's a state space. State space is formed by the states, the actions, and the transition is represented in a graph. A node is a state, so A, B, C, D, E, F, G, H, I, J, K are all nodes, and the lines between them are known as paths or links. So those are what represent actions. So there are two types of costs here. First is the goal cost, goal test. So you check if you are at your goal yet. The second is path cost. So the energy or the amount you expend to get to a specific node is known as your path cost. So let's say you're trying to get to B from A, there's going to be an associated path cost to that. Obviously, in this diagram, it's not specified because here they're all uniform and zero, but we'll see path cost later. So the first is just tree terminology. A here is the root node, and the parent nodes are the ones that we have that have children. So B and C are children of A, D, E, F are children of B, GH are children of C, K is children of K is a child of G, etc. So if you have no children, you're known as a leaf node. So here the leaf nodes are I, J, and K. And the degree of a node is the total number of children. So here the degree of node G is going to be K. So here, as you can also notice, there are 4 levels. The first is the root node, and that's level 0. And then there are 3 additional levels. So each level is basically a layer of children. Yeah, that's pretty much all. The height is the longest path to the leaf node. So the height of this whole tree is ABEI or ABDI. Regardless, the height is always going to be the same. Um, yeah, that's all. So there are a few types of search algorithms. The first is uninformed. That is, you blindly follow an algorithm and you try to brute force it. The second is informed. That is, you use some sort of domain knowledge. So first we look at uninformed search algorithms. The first type is breadth first search. So expand level wise from root node left to right, or like the shallowest unexpanded node is the formal definition. But the priority you need to remember here is that in any type of uninformed search algorithm, you always have to prioritize the left over the right. So here your path will be to go level by level. So A, B, instead of going down to D, you'll go to C because you want to explore that level fully. So A, B, C, D, E, F, G, that's how you travel. The blue line indicates the path here. So this will provide a solution at all points in time, but it requires a high memory and time because you have to go through all the nodes at some level. So, okay, so there are 2 factors here that we need to consider. The first is time complexity. So in time complexity, there are 2 things to think about. The first is B, which is a branching factor. This is the average children per node. The second is D, which is depth. Now, we don't really need to worry about that. It's probably easier to remember what time complexity and space complexity are for each of them. But just for a brief definition, um, the time complexity is the amount of time that it probably takes to go through every node and arrive at the goal. The space complexity is the amount of memory that you store at the last state before you arrive at your goal. So this memory obviously changes with each node, but here both time complexity and space complexity are going to be O of B to the raised to the power of D. And you can see the mathematical expression here. O of refers to the 1 plus part that is there. So it's 1 plus B square plus dot 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 BD. Second is depth first search. So here you expand the root first and you go to the greatest depth possible. That is, you go to the last node that is available. And then once you realize that the goal node is not there, then you're going to backtrack to the next top node that is there. So here you're going to go S to A to B to D. And then you're going to realize that the goal node is not there. So you'll go back to C, which is the closest unexplored node on top of it. Then you're going to go to its children because you have to explore like the maximum depth. So you'll, well, no, not really. That was wrong. So you'll go S, A, B, D, and then you'll go to E. because that's the closest unexplored node. And then you go back up to C, and then you go to G, then you go back up to C, then you go, well, G is the goal node, so you don't need to go back up, but that's the point. Basically, you go from S to A to B to D to E to C to G. So yeah, time complexity is also going to be O of B raised to the power of D here. Space complexity is probably not going to be the same as breadth first search because it's going to use a lot less memory. Or wait, no, it uses more memory. But regardless, easier to remember is it's O of BD. Depth limited search is just a type of depth first search where you solve the drawback of going to infinity nodes before you arrive at a goal node. So you set a limit saying that here's the maximum depth I want you to go to. So let's say the limit is 2. You're not going to be allowed to traverse down more than 2 nodes. So on the right, if you see here, um, if C equals 2, it means that you're only allowed to go up till D, A to B to D. Since you've gone down 2 levels now, you have to check all the nodes on that level and then the levels above that. But here is where your depth limited, right? If G was your goal node, then you probably aren't going to reach your goal node. But if E was your goal node, then you're reaching it much more optimally than a depth first search would, because you would have otherwise gone from A to B to D to G to H and then come back to E. Now you're just going to A to B to D to E. But it can also be less than optimal when your solution is below your depth limit. Here, the time complexity is O of B raised to the power of L, and space complexity is O of BL. It's the same as depth first search, you'll notice, but the only difference is instead of D, we're using L because L replaces D here, the limited depth instead of depth. The next is uniform cost search, and here you just want, here's where like the path costs that we discussed here come in, right? So you see that there's a number on each of these. So 2, 1, 3, 2, 5, 1, 4, 3, 1, 2, 5, 6, 3, 2, blah, blah, blah. Here the goal node is the one at the bottom, the Z. So the first thing you do is you create a priority queue and you add in your root node immediately. And then you expand its children. So here the children of the root node are B, T, O, E, and P. So you add all of them in the order of least cost. So here you see that T has the least cost, which is 1, and then E has the next least cost, which is 2, and then O, and then B, and then P. So you add in that order, and then you remove C. So you've expanded C, you've added its children into the list. So here you will see that the next is T, B, E, O, P. And then you do the same thing. Since T is the least cost, you're going to expand T. But since there's nothing to expand, there are no children, T is childless. So we throw T aside, we expand the next best, which is E. So here we see that T is gone, and then we expand E, which has a child, which is G. Wait, what did I do here? 3, E2, 3 here. Wait, I lost track, honestly. O3, why did I expand O here? That's kind of dumb. Huh. Hmm. I don't know. You're probably going to want to expand E here, and you're going to arrive at your goal node immediately. But let's, for the sake of argument, pretend that. Oh, wait, that's because G is not the goal node. Okay, never mind. So I was right. You expand E and then you put G at the back because G's value is now 5 plus the cost it took to go to E. So it's 5 plus 2, which is 7. So it goes at the back. And here, O's cost is going to be lower. So you put O at the front and then you expand O, which comes to ing, and then you add those into the list as well. So whenever you open something, you remove it from the list. And when you add something in, make sure to take the cumulative cost of the path cost that it took. So if you're adding in I, for example, the path from O to I is 1, and the path from C to O is 3. So 3 plus 1 is going to be 4. So the cost for I is going to be 4. And that's how you're supposed to arrange it, least to highest cost. And eventually you will arrive at, yeah, that solution path. So here there's another example. probably an easier one to go through, but you'll see that you expand B first because it's the least expensive to expand, and then you, well, go on like that, right? You add ABC first, and then you expand. Oh wait, I don't know what happens here as well actually. SCG. Hmm. I don't know actually. I don't know what's going on. Hmm. Hmm. It's interesting. Okay, we'll see. You get the principle of uniform cost search. That's what we need to worry about. Clearly, I've forgotten because my exam finished, so everything exited in my head. But yeah, the next type we'll move on. Iterative deepening search. Here, this is basically depth limited search, but you repeat it for increasing depth. So the first step is you take your depth limit as 1. And your path is going to be A to B to C because the maximum depth you can go to is 1. And then you take your limit as 2. Then you're going to be able to go from A to B to D. And then you can traverse to E and then to C to F to G because they're all below the limit of that depth. Then after that, you so on. It's pretty simple, the path here. Basically, you have to repeat DFS with the increasing limit until G. Why is this a thing at all? Is because it combines the optimality of breadth first search with the lesser memory requirement of depth first search. So the depth first search um, needs less memory to operate, and but BFS is more optimal. So you want to combine both of those, and you go depth first search here, but you essentially use the same principle that a depth limited search would. Last is bidirectional search, which you probably won't see a lot of, but basically the principle is you do breadth first search from the top, and then you do depth first search from the bottom. So there are usually, well, if there is a depth that is D, that's not depth equals 2. That shouldn't be that. That should be depth equals D. So if you see here in the diagram that D is 1, 2, 3, 4, then you're going to want to do breadth first search from the top for 2 nodes, which is C and G. Then you're going to want to do depth first search from the bottom, which is the small c here and O. These are small alphabets because I ran out of like the big ones. But basically that's what you do. So the left column is you doing depth first, breadth first search. Obviously the first is A, the second is A, B, C, and then A, B, C, D, E, F, G. And then you do that here as well. You do depth first search here, so you go C first, and then you increase the limit, you go CO, and then you increase the limit again, you go COG. Time complexity, space complexity, both the same. D by 2, obviously, because depth here is D by 2 for each part of the algorithm. So this is optimal when the branching factor is uniform. I honestly don't know what that means, but who cares? Like it's a bit of theory you probably have to remember. There's a small table here that compares the time and space complexity. They will probably ask for this. So find some way to remember that. Um, The next is an informed search algorithm. So earlier we covered uninformed. Now we're going to look at informed. Here's where a heuristic function comes in. This is h of n, which is the most promising path that estimates your closeness to a solution. This is not a true value. The heuristic function is always going to be an estimate of how close you are to the goal node, right? So this is necessarily not the best solution. It's just an estimate. So having established that, greedy first, best search. So you create 2 lists here. The first is an open list, and the second is a closed list. So the open list is one that you generate, and then you keep open while you're applying to the question. The closed list is the one that you close. So when you expand something and take out its kids, you close it. So here, the open list initially starts with the root node, as you can see, and the closed list is empty. Then you expand S, and the open list has A and B, which means that the children are here in O and the parent is in C. Then you expand A, which, wait, no, you expand B, I guess. Why are we expanding B? Oh, because we have the h of n here. So we want to expand the ones with the least heuristic function because we want to reach the goal node with the least cost possible. So here the cost of B is 4, the cost of A is 12. So we want to expand B first in the open list of A comma B. So we expand A comma E comma F, our open list items, and then we have S comma B because we've already expanded both S and B. And then similarly, you go on and then you see that in E and F, F is probably your minimal H of N, which means you expand F, and you put F in the closed list, and then you get I and G, and then you've gotten the goal node. So your path is S, B, F. That is the final path. Space and time complexity are here. That's pretty much all a greedy first best searches. Next is the A star algorithm. Here you find the shortest path with both HNN and the cost to reach node. So here's where a fitness function is defined. So we remember G of n from earlier, which is the cost to reach a node n from the root, which is basically the path cost, right? The 3 and the 8 and the 15 and the 7 you see are all path costs. H of n is the heuristic function, which is the estimate of how long it'll take to reach the goal from that node. So for example, if B's B's H of n is 4, then the estimate for you to reach G from B is going to be 4. But you will also notice, I mean, okay, apparently I is the goal node here, but you see that I has a heuristic function of 0, which means the estimate is going to be 0. It's always going to be 0 for the goal node. So if G was a goal node here, then G's estimate for Hn will be 0. All right. So A star algorithm combines both of those. So you want to minimize the sum of this fitness function. So here you'll notice that there's a diagram and we've been given path cost and we've been given heuristic function as well. You have to operate on the sum of these. So the first is obviously expand the root node, you get B and C as its children, and you close the root node. And then you see that from B and C, from going from A to B is 1 plus whatever the h of n of b is, which is 6, which is 7 total. So 1 plus 6 is 7. For C, it's 4 plus 4, which is 8. So you want to go to B because it's cheaper to go to B. So we expand B. Then we get two children, which are C and D. So we close B and put it back into C. Then we have D and C as the children that are opened up. So here, which one do we want to expand next? For going from B to C, it's 2 plus 4, which is 6. For going from B to D, it's 3 plus 3, which is also 6. So priority here is always going to be the one that takes you further towards the goal node. So there are a few priorities that comes and applies when a tiebreaker happens. Usually it's left to right, but it's also sometimes what you have to achieve, what takes you lesser time to achieve. So honestly, it doesn't really matter, but here we go ahead and pick D, and we again do the same thing. So for going from D to F, the cost is 2 plus 1, which is 3. And then, well, going from D to G is 4 plus 0, which is already greater. So we go from D to F, then we expand its children, we get G, and then we have the goal node. So that's what happens. The path is now ABDF because that's the cheapest way to get to the goal node based on the sum of, well, the G of n and the H of n. The difference between this and this is that here you only consider the H of n, here you brought in G of n as well. So you consider both path cost and the heuristic function. So that is your path. So here there's another example of your H of n. I'll zoom in a bit. I think this is 8 here, but it's basically the same thing. Finally, we have admissibility. So when is a tree admissible? It is admissible if all its nodes are admissible. And when is a node admissible? So we just discussed a heuristic function. So that heuristic function is the estimated cost to reach a goal from your node n. So what you have to ensure is that this estimate is always less than the actual value. So h of n is basically a guess, and h star of n is going to be the actual value. So you want to ensure that you're never overestimating the value of h of n. So for every single node, you have to make sure that the time that it takes to reach, or the cost that it takes to reach that node, is always going to be overshadowed by the actual estimate that you have. So the effect of admissibility on A star we'll discuss, but that's the basic meaning of admissibility. So we'll look, I think example will make it easier. So you check on all nodes. So you basically draw a table of all the nodes. So here all the nodes are S, A, B, and G. So you draw all of that. The H of n for each of them is given in blue. So 7, 5, 1, and 0, 7, yeah, 7, 1, 5, 0, same thing. And then the way you calculate H star of n is by going from G to that node. And that's, you should take the shortest path always. So to go from G to A, your cost is 4. So the head star of n is going to be 4 because that's what the actual cost was to get from G to A. To go from G to S, the cheapest way to do that is going to be to go from G to A and then go from G to A to B and then B to S, because 1 plus 2 is 3 and that's less than 4. So it's going to be 7, which is equivalent for the S nodes head star of n. So you'll notice that as long as your h of n is always lesser than or equal to, then this network is going to be admissible. But here you'll notice that um, there is a violation. So B, the head star of n here is 1, and 1 is always, well, 1 is greater than 3. So you'll see that the path cost to go from G to B is only 1 here, and it violates the principle, therefore this circuit is not admissible. So there are two small things to note. If a tree is admissible, then the A star algorithm is always going to be optimal for it. You never overestimate the h of n value. But the second thing to understand is that it reduces your search space and the memory that you need to, well, do the whole thing, I guess. The next thing we look at is propositional logic, which is module 3. Um, Bunch of definitions. Statements of true or false are propositions. Statements are variables connected by connectives. Not is not. Implication is P arrow Q, which means if P then Q. Logical and, logical or. Biconditional is B double arrow Q, P if and only if Q. Operator precedence is also quite intuitive. There's an example here. P is it is hot, Q is it is humid, R is it is raining. If the statement given is if it is hot and humid, then it is not raining. Then, well, if it is hot refers to if P, and humid refers to Q. So, and then it is not raining. This is not R. So P and Q arrow not R. So this basically means if P and Q are true, then not R is true. The rules of inference is a bunch of theory that you probably don't need, but modus ponens is basically if you have A and if you have A arrow B, then your conclusion is going to be B. Is a quite simple example of this here. That is A, it is raining, B, if it is raining, then Rahul fails. The combination of this is that Rahul is always going to fail because rain has been established. So that's how you conclude B from A comma A star. So if these two statements are given, you always get B, which is Rahul fails. Second is double negation. Negation of negation is cancel each other out. Unit resolution is again a similar thing to modus ponens. Resolution is what we'll look at now. So the only two questions you're going to get from this module are converting propositions to resolution and converting FOL to proposition to resolution. So the first is you replace these are just simple steps, honestly. These three steps are all you need. If you see A double arrow B, you replace that with A arrow B and B arrow A. The intuition is simple. This is if and only if. This is the equivalent of if and only if. You see two ifs and you see and. It's the equivalent. Second is you replace if A then B with not A or B. So this is something that you need to do and something you need to remember. It'll become pretty easy to remember. Yeah, and then these are De Morgan's laws. You should probably know them by now. Distributive law, commutative law, De Morgan's law once again, associative law. But yeah, you can take a second look at that. So how do you convert to CNF or conjunctive normal? P, if P then Q, then R, you apply the principles that we discussed here. These two steps are all you need. So if P then Q, then that converts to not P then Q, not R, because there's an if here as well. So you resolve this arrow first, then you resolve the arrow inside. So not of not P or Q or R, then you bring the negation inside. that becomes P and not Q because the sign flips when you bring the negation inside, or R. That's pretty much, you rearrange that and there's your answer. That's pretty much a similar process across all three of these questions. So that's pretty simple. That is not what you will be asked though, unless your teachers are feeling lenient. The second is resolution. So how do you resolve things? So you're going to be given a bunch of statements and you're going to be given a goal. They'll ask you to prove the goal if the statements are true. So the statements that they give are known as premises. The goal they give is known as a conclusion. So first you convert the CNF to this form, the resolution form. Then the next thing you do is take the negation of the goal and add it to the list of premises we have. Then we apply the resolution rule, which is when you have A or X and not A or Y. So basically, you have A in one statement and not A in another statement, and you have two variables here. Then the result of these two is going to be X or Y. And then the way you do that is you keep simplifying these. And then if you get an empty clause here, it's a contradiction, which means your conclusion is logically following because you've taken the negation. Now, this is annoying to understand, but an example will make it fairly intuitive. The first question, the premises you are given are fourfold. The humidity is high or the sky is cloudy. The second premise is if the sky is cloudy, then it will rain. The third premise is if humidity is high, then it is hot. The fourth premise is it is not hot. The goal that you are given that it is not going to rain or it will it will rain is your goal. So first we convert from English to logic. The humidity is high or the sky is cloudy. Let's say P is humidity is high, Q is sky is cloudy, R is it will rain, S is it is hot. So based on these four premises, we make up variables that makes it easy for us to assign. So humidity is high or sky is cloudy. First premise gets assorted to P or Q. R becomes, sorry, if humidity is high, then it is hot, then that becomes Q implies R. Similarly, sorry, if sky is cloudy, then it will rain becomes Q implies R. If humidity is high, then it is hot becomes P implies S. And then it is not hot becomes not S because you defined S as it is hot. It doesn't really matter how you define them as long as you're using the same logical expressions to go consistently. So the goal here is it will rain. So we have our list of premises, which is these four, P or Q. Q implies R, P implies S, not S. The goal is it will rain. Now we know that we have to negate the goal and add it to the list of premises. So the negation of this goal is going to be it will not rain. How does that translate? We have R is it will rain. So it will not rain will become not R. So the fifth premise that we add then is not R. So the list of premises now is P or Q, not Q or R, not P or S, not S, and not R. Because we've converted these into this. So P or Q is P or Q, obviously, but Q implies R is converted to not Q or R, following the same rule that we discussed um, somewhere here. Yeah, here. But yeah, that's pretty much all. And then you apply the resolution rule, which is if you see two statements that have uh, in which one of them has a statement A and the other has a negation of that statement, you apply OR to that, then your result is going to be X or Y. So here we see that P or Q, this statement, and not P or S have P and not P. So result is going to be Q or S or Q, the same thing. Similarly, we take this statement again, we take not S, and since this is Q and not S is technically not S or it'll be 0 because not S or 0 is not S. So it'll be Q or 0, which is Q. Again, same principle applies. Here, not Q, and then here we have a null set because we take the not Q and we use it with the Q that we already have from here, then we get a null set. So the rule here is a bit of arbitration, but what I have understood is that you can use any one term that you get here as many times as you want. And you don't need to use all the terms here. As long as you use any combination of these five and arrive at a null set, then you've proven that the conclusion is logical because we've taken the negation of it. And if we negate it and take the contradiction of the negation, and that just means we get the actual conclusion following. So that is for resolution from proposition. The second sort of question you're going to get is first order logic. This is another sort of conversion. Um, Propositions are only capable of true or false statements, but first order logic is going to define everything. So every person is XYZ, some people are XYZ, etc. So this is also known as predicate logic. So if some examples are here, X is a girl, which means girl of X. This is a function. So you see that constants are one, two, Joe, cat, their names, variables are variables. Predicate is basically describing that variable. Function is a verb usually. So if you're someone's mother, then you're John's mother here, I guess. But yeah, so here's where quantifiers come in. The first is a universal quantifier, which means, well, this is the symbol for universal quantifier. Comes into play when you talk about for all and every. So if you say all employees, it means for all, that is a symbol's meaning. For all X, employee of X, which means you are an employee as long as you're X. So, for example, all professors are people, which means for all X who are professors, they are also people. So if you are a professor, then you are a person or you are people. The second type of quantifier is existential, which refers to some, at least, basically everything doesn't apply here. So you see here, even and prime numbers, there's an existential quantifier here. All students are smart is again going to be universal quantifier. So whenever you're converting a statement from English to FOL, if you are converting a statement with every, all, etc., you're going to use the quantifier that's universal. And when you're using that, you always want to use the arrow. That is if then. So you always use this for um all of X, and then you use and. So you'll understand in just a second what I'm talking about. So the first question is, there is a student who is smart. For all X, where a student, well, there's a student who is smart. So when there is a student, they are smart. So student is smart. Every student knows arithmetic. Oh wait, no, that is not. Yeah, for here you see that some, it's not all. So if you are a student, then you are smart. So the and is used here instead of an arrow. That is because it is an existential quantifier. For a universal quantifier, you'll use an arrow because that's how it follows, right? Every student knows arithmetic. So if you are a student, then you know arithmetic. So student of X implies knows of X comma arithmetic. So knows is a function here, it's a verb. Similarly, some students know arithmetic is going to translate to sum of X or whatever existential quantifier of X. But you are both a student and you know arithmetic. So and is used here. So there are some more interesting examples. I would say go through all of them. They're pretty important to understand how this follows. This is more of a listing all topics and sorts of questions that are going to show up rather than, oh, everything is going to be taught in depth, I guess. I mean, I'm just revising this for my own sake. I don't know why I'm doing it after the exam. But, oh, there's FOL loss, two small loss here. So not before a universal quantifier is going to be an existential quantifier, and then not inside. So you take the not, put it inside, and then you switch the quantifier here. An example of this is the negation of all dogs bark, which is not all of X, is going to be some dogs do not bark, which is the equivalent of this, right? Some and then not comes in. The same happens here. If you have a negation before the quantifier, then you put the negation inside and you switch the quantifier to a universal one. Resolution we also discussed already. So that's it for module 3.